This video covers using linear relationships, and our learning goal is to identify and use linear relationships. Now, linear relationships exist between the two variables that involve a constant rate, and what I mean by that is it's going up by a constant rate each time. As x goes up by 1, y goes up by 2, for example, all the way along. Now, that's represented by a straight line graph. And we know from the last video that we have our rise over run, which is our gradient. So when we have a straight line graph, that rise over run is always the same. So we have a constant rate. So first question, identify and define the two variables in each of the following. The volume of water in a water tank increases during a day of heavy rain. So our variables here would be volume of water and time, because that volume of water is going to change over time, and our volume of water is going to depend on time. So if we're going to graph this, our volume of water would be on our y-axis and our time would be on our x-axis. Next, the average speed of a car as it travels over a distance. So we've got the average speed of the car and it's over a distance. Now, average speed of the car is actually a rate. Okay, so we could actually look at this in two ways. We could have average speed of the car versus distance. Okay, so what is our average speed at certain distances? Or more likely what you're going to see is distance and time. And in this case, our gradient would be speed, because it's a change in distance, our rise, over the change in time. Okay, define the variables in the linear relationship with the following. The cost of a building project at a school consists of a $1,000 fixed cost to cover the materials plus labour, and that's $30 per hour. So our variables, we're going to work out our cost. Okay, that's going to be in dollars, and let's let that equal C. Now our cost depends on our fixed cost, but then we have a charge per hour. So our cost is going to depend on how many hours. So our other variable is time, okay, which is our number of hours. So let's let that equal T. Now if we think about the last thing we did, we talked in our last video, our equation was our fixed amount. What is it initially? No matter what, our cost is going to be $1,000 because it's a fixed cost. And then for every hour, it's going to cost us another $30. So that's going to be 30 times by however many hours we've got. So our formula is 1,000 plus 30T. Okay. Next, an electrician charges a $50 call-out fee and a $30 hourly charge. Pause the video and have a go at this one yourself. Did you actually have a go at yourself? If not, pause the video and have a go. Okay, our variables. Again, we want to know how much he charges. So our charge in dollars, let's let that equal C. And again, because it's a $50 call-out fee and then $30 an hour, our other variable is going to be, well, how long is he there for? Our time in hours. Okay, let's let that equal T. So just by previously, our charge will always be, no matter what, it's going to be $50. It's going to cost $50 no matter how long the electrician's there. And then it's going to cost an extra $30 per hour. So that's 50 plus 30T. Next, this is from the worksheet. A tap is left dripping at a constant rate. The number of litres of water is shown in the table below. So look at your worksheet so you can fill this in. So we have a table, 0, 0, okay, 210, 630, and 11:55. Okay, and we should label our axes. We have number of hours, H, and number of litres is in litres. This is our variable W, this is our variable D. So we need to draw a straight line through these points. Okay, so you can see my straight line. I've put an arrow on it because it keeps going. Okay, so that's why the arrow is on the end of the line. And you can see it's a straight line, which means we have a constant rate of change. It's linear. So is the relationship linear? Yes. How much water would be wasted in 12 hours? So we come across to where 12 hours is, which is here. Okay, we need to follow the line up and then go across. Okay, so number of litres is 60 litres. Oops. How long will it take to waste 20 litres of water? Well, now we need to start on our y-axis at 20 litres, go across, go down, and that's at 4 hours. Is it sensible to join our points? Well, yes, it is, because our number of hours, even though they're exact numbers, in between, we've still got water dripping. So at 3 hours and 5 minutes, the water is still dripping. Okay, so we should have a straight line through the points. Now, if we're writing a rule for the relationship, we always go with our fixed amount, like what is it at 0, our initial amount, sorry. And our initial amount, or our y-intercept, is 0 in this case. Okay, and then we need what our rate is, what our gradient is. So our gradient, if we draw a line here, we can have a triangle. Our rise is going to be 10, 25. So that's our rise. And our run is from 6 up until 11, which is 5. Okay, so our gradient, or our rate, is rise over run, which is 25 over 5, which is 5, and it is positive. Okay, you shouldn't work across, you should work down, but I don't have enough room. So our formula, our W, which is number of litres of water wasted, is going to equal our initial value, which is 0, plus 5 times however many hours. So W equals 5D. Next, a Year 8 class chose to support a cancer research charity by organising a school concert as a fundraiser. The following table shows the total money raised as the number of tickets sold increased. Their teachers also made a donation to the fund. So let's fill in our graph. Number of tickets sold, 50, which is $2,000. 70 is going to be 2,200. 160 is 3,100. And then 180 is 3,300. Okay, we now need to join the dots. Okay, so you could probably draw a better diagram than mine because you're not on a computer. We need to label our axes, number of tickets sold, which is our variable T, money raised, which is in dollars, and that's variable M. So, is the relation linear? Yes, it's a straight line. How much money was raised if 200 tickets are sold? So 200 tickets is here, all the way up, all the way across, so that would be $3,500. How many tickets would need to be sold to make $3,500? Same answer, 200 tickets. Is it sensible to join the the dots. In this case, no, because you can't sell anything besides whole number tickets, okay? So you can't sell 50.2 tickets, but we're going to join the dots because it's an easier thing to see. Like, it makes sense to do it in the fact that to draw individual dots would be silly. Write a rule for the relationship. What's our initial value? Our initial value is here, so that's our 1500. So when we're writing our relationship, the money raised, M, is going to equal the initial amount, which is 1500, plus how much is it costing per ticket. I'm going to do my gradient over here, so I don't have a lot of room. So we need to do, sorry about that, our rise over run. How about we just do it in regards to this whole big triangle? So our run is 200, our rise is 3,500 minus 1,500, so that's 2,000. Okay, so our gradient is rise over run, which is 2,000 over 200, which is 10. So this is going to be, for every increase in X, I get 10 of Y. So it's 10 lots of T. How much do the teachers donate? Well, the teachers gave a fixed amount. That has to be that $1,500 because that was our initial amount. What now? Complete the exercise. Exercise 6.4, page 376, questions 1 to 4, question 6 and question 9.